Hi, and welcome to this live reading from The Hand of God, From Oppenheimer to Hypersonics, a crash course on nuclear weapons and humankind's most dangerous game by Paul McCarthy. And this is presented by Itsy Bitsy Book Bits. Chapter 1, The Philosopher's Stone, Nuclear Physics. The unleashed power of the atom has changed everything except our thinking. Thus, we are drifting toward catastrophe beyond conception. We shall require a substantially new manner of thinking if mankind is to survive. Dr. Albert Einstein. Regarding the history of nuclear weaponry, I will go back a little further than some conventional sources might. While many point to August of 1942 as the key birth date of the technology, we should go back to the 1800s to establish a solid foundation. There, we'll take a peek at the formation of the field of nuclear physics, which stands as the foundation of the bomb. Without nuclear physics, you don't have nuclear weaponry. This section of the book will be one of the most science-heavy. Still, I will try to keep the concepts and the wording as basic as possible so that everyone can understand the information necessary to process the foundational nature of what makes nuclear weaponry tick, while hopefully not being overly dull. Without getting too in the weeds, as this is not a science textbook and not intended necessarily to expand the horizons of nuclear physicists or historians of science, we can start with Dr. Einstein's famous 1905 equation, E equals mc squared. In simple terms, this equation is about how much energy an atom has. The E stands for energy, the m stands for the mass or weight of the atom, and the c squared, Latin celeritas, which means speed, stands for the speed of light. The equation says that if you want to determine how much energy an atom has, you can do it by multiplying its mass by the speed of light squared. To put it another way, mass and energy are the same physical entity and can be changed into each other. The mc squared part of the equation is the rest energy of an atom that is potentially available for conversion to other forms of energy. That sounds complicated, but all it really means is that the more mass an atom has, the more energy it has too. So why is this equation so famous? When scientists figured out this equation, it helped them understand how the sun and other stars produce energy. And as you'll learn later, the energy contained inside an atom is nearly unbelievable. A mass the size of a penny, if converted to energy, can power the New York City metropolitan area for a minimum of 2 years. So in many ways, Einstein's equation set the foundation for utilizing the power contained within atoms. As we now know, this mathematical foundation ultimately led to the creation of the most powerful weapon in the known universe. But as I said, we'll step back a little further to the late 1800s and the work of the French engineer and physicist Antoine-Henri Becquerel. Becquerel was fascinated with and focused on the study of phosphorescence, which is the examination of materials that absorb and then emit light for an extended period of time. Examples of phosphorescent material are glow-in-the-dark stickers or signs. As a kid, you may have had glow-in-the-dark stars and planets on your ceiling. Those are typical examples of phosphorescent materials. Don't worry, they're not dangerously radioactive, as modern scientists and corporations know not to use such materials. In late 1895, another scientist named Wilhelm Conrad Röntgen identified the X-ray, a curious and little understood phenomenon at the time that was named as such because X stands for something unknown in the field of mathematics. In short, as you probably know from your own doctors and dentist visits and the medical imaging you and your family may have undergone, X-rays are a type of penetrating radiation that can pass through certain objects. They're useful for many things, but are known most popularly for their medical applications. Although they had been produced in experiments as early as the late 1700s, they were not yet understood or specifically identified. Back to Becquerel, our French engineer. After learning that Röntgen had identified an invisible being that could pass through paper, Becquerel wondered whether the phosphorescence, again glowing, he had observed in certain materials was somehow associated with these mysterious X-rays. For example, he thought some uranium salts might emit X-ray-like radiation when charged with bright sunlight. With regard to his hypothesis about X-rays, it turns out Becquerel was at least partly right. The uranium was emitting energy, but it had nothing to do with the sun charging it. In fact, Becquerel discovered by May of 1896 that the energy produced by the uranium was independent of any outside or external source of energy like the sun. Interestingly, uranium's radioactive effects had also nearly been discovered in the mid-1850s through observational experiments on photographic materials, namely that the uranium would expose photographic material even in a dark room. Still, the science was not yet established, and the conclusions were not yet direct enough to identify radioactivity. We know now that uranium is a common radioactive element, elements being the basic building blocks of matter such as hydrogen, carbon, helium, etc. I won't get into the nature and description of uranium salts, as that's a technical discussion beyond our explorative scope here. For these purposes, though, if you're unfamiliar with radiation and radioactivity, radiation is the transmission of and emission of energy through particles or waves that travel through space or even materials. X-rays are a type of radiation everyone is familiar with. We'll talk more about radiation as we progress through the discovery of nuclear physics. Following in the footsteps of Röntgen and Becquerel was a daring, ingenious chemist and physicist by the name of Marie Curie, who discovered, using her husband's electrometer, a device used for detecting an electric charge, that energy coming from uranium could cause the air around a sample to conduct electricity. Dr. Curie observed that the energy emitted by the uranium was constant and that minerals with more uranium emitted stronger rays. She hypothesized that the rays coming from uranium could be unique to that uranium, that they were actually an atomic property of the element uranium itself, built into its atoms and part of its very nature. By 1898, Dr. Curie had discovered that thorium also emitted rays and that this emission was likely an atomic property of the element. That same year, Marie and Pierre Curie discovered the elements polonium and radium, Latin for ray. In addition to discovering various radioactive elements, they created the word radioactivity to describe the phenomenon they observed. Although not the subject of this book, what would eventually become an essential discovery to medical science is the Curie's revelation that radium could destroy cancer cells more rapidly than healthy ones. Eventually, this would lead to advances in cancer treatment. I mentioned this aspect of the Curie's work because the effects of radiation on the human body and the environment are an important aspect of nuclear weaponry that we'll discuss later. By July of 1934, Marie Curie would ultimately die from aplastic anemia, a severe blood disorder in which the body cannot produce adequate levels of blood cells, believed now to have been a product of her exposure to radioactive elements throughout her career. Dr. Curie's remains were so contaminated with radiation that she had to be sealed in lead lining. Her papers from the 1890s are similarly packed in lead-lined boxes and require those consulting them to wear personal protective equipment or PPE. At the time, science did not have the foundation to comprehend the dangers of radiation exposure fully. While Dr. Becquerel's cause of death is unknown, he passed at age 55, and it was noted that he had burns on his skin, likely stemming from his handling of radioactive materials. Ernest Rutherford's studies moved the field rapidly forward around the same period as Dr. Curie's and Dr. Becquerel's experiments. His accomplishments would eventually lead him to be dubbed the father of nuclear physics. In 1899, he discovered new types of radiation, alpha and beta rays. Before Rutherford's work, atoms, the basic building block of matter, were understood to be indivisible. That is, they were believed to be the smallest form of matter and could not be broken up. In 1903, he correctly observed through his radiation experiments that, in fact, radioactivity was a result of the disintegration of atoms into other matter. However, the nature of that matter was as yet not understood. By 1903, he had discovered a new type of radiation with far greater penetrating power, coined the gamma ray. Gamma rays are similar to X-rays in that they are photons of pure energy. They have the same basic properties, but come from different parts of the atom. While X-rays are emitted from processes outside the nucleus, gamma rays originate inside the nucleus. X-rays are also generally lower in energy and therefore less penetrating than gamma rays. Dr. Rutherford's most famous discovery came from the gold foil Geiger-Marsden experiment conducted in 1909 with Hans Geiger and Ernest Marsden. By firing alpha particles at gold foil, this experiment showed that atoms were built of a small positively charged nucleus making up most of the atom's mass, surrounded by an expansive cloud of low mass, negatively charged electrons. I'll explain alpha particles later as they become important in the transition from hypothetical to practical nuclear physics in future decades. Rutherford also concluded that a hydrogen nucleus was a fundamental building block of all atomic nuclei, plural for the nucleus, and called it the proton. These experiments led to the understanding that atomic nuclei also contained neutrons, which provide mass but have no charge. Thus, you have the proton, the neutron, and the electron, the basic building blocks of the atom. James Chadwick, who worked with Rutherford, is ultimately responsible for discovering the neutron. This discovery would be critically important to nuclear power and atomic weaponry, as neutrons are the proverbial bullet that sets off a nuclear reaction. Stepping way back into history for a moment, fundamental to understanding nuclear reactions is the concept of transmutation, which is the conversion of a basic chemical or element into one of an entirely different nature. While alchemy has a long history dating back as far as ancient Egypt, it's most commonly known for the search for the Philosopher's Stone, first mentioned by Zosmius, alchemist of Panopolis, a Greco-Egyptian alchemist in the 4th century AD. Historical analysis ties the roots of the concept of the Philosopher's Stone to ancient Greek philosophy. Regardless of its true origin, the Philosopher's Stone was believed through a process called chrysopia to be capable of turning base metals such as mercury or lead into gold. We know now that lead and gold are basic elements, so no chemical process can turn one into another. That said, it was simply the case that alchemists did not yet have the science available to them to understand how to transmute elements. The power of transmutation lies instead with nuclear technology. Enter Frederick Soddy. Soddy, who also worked with Rutherford, showed that the radioactive decay of radium would produce helium gas. This was demonstrated by taking a sample of radium and enclosing it in a glass envelope within an evacuated glass bowl with no air or other material present. An analysis of the bulb later demonstrated helium to be present, showing that some of the radium had decayed into helium, which was not present in the original sample. This was an early demonstration of transmutation, one element turning into another element. In addition to his contributions to understanding transmutation, Soddy similarly discovered that certain elements can have different isotopes. Understanding isotopes is essential to understanding nuclear weaponry, and we'll discuss them further later, but the general idea is that isotopes of the same elements can have the same chemical properties while having different physical properties and masses. Most everyone knows about the element hydrogen. Hydrogen has an atomic weight of 1, that is to say, it has 1 proton in its nucleus and no neutrons, so an atomic weight of 1, and multiple isotopes. One of these hydrogen isotopes is tritanium, hydrogen 3, which has 1 proton like hydrogen, but also has 2 neutrons in its nucleus, giving it an atomic weight of 3. Tritium is often used to light up exit signs without the use of batteries or electricity. Another isotope of hydrogen is deuterium, hydrogen 2, which has 1 proton and 1 neutron, giving it an atomic weight of 2. Many isotopes are not stable and fall apart in the process of radioactive decay. These radioactive isotopes, ones that decay, thus giving off energy, are known as radioisotopes. As rapid understanding of radioactivity and the nature of the atom began to develop in the late 19th and early 20th centuries, scientists began to understand more and more about how atoms interacted with each other and the processes that were taking place inside atoms themselves. This understanding drove researchers to start to express concern and even fear about the potentially limitless power of the atom.